EMF. Now, I can't see you, so give me a shout if you saw the aurora recently. Give me a shout if one of your friends saw the aurora recently. See, we all know if one of our friends has seen the aurora, because the next day they will have come and told you with a stupid smile on their face, I saw the aurora. Now, this talk is going to be based on what can we see in the sky? What is it that makes us go, yay, I've seen the thingy in the sky, wasn't it great? Why do we smile like that? And what are those things that we're actually looking at? I'm Lucy Rogers. In a previous life, I've been a judge on BBC Robot Wars. I've written a book on rocket science, and I have made a fartometer that was on the IBM website homepage. Only time fart has appeared on that website. I am not renowned for being in touch with my emotions. Engineer, scientist, me, not really. But I was discussing the other day with one of my friends about what is it that makes us go, oh look, there's a thing in the sky. Now, do you remember a couple of years ago that blue, black, gold dress thing? Yeah. So that sort of put it back into our consciousness that we see colour differently to each other. Well, we also feel emotions differently to each other. So my friend was saying, oh yeah, when I saw this thing in the sky, there was awe, there was wonder. I was like, well, what's the difference between awe and wonder? So, being geeks, we looked it up. We have a spinning beach ball of death. Oh. And somehow we're all the way through the slide deck. So my friends and I got out this book. Had nothing to do with rainbows. Worked in the green room. We got out this book, Brené Brown. Don't know if you've read it. And it said that although we use the words wonder and awe interchangeably, the researchers use them slightly differently. We're nearly there. There we go. Let's have this one. Wonder inspires within us the wish to understand. But awe inspires us to just let it shine and then to unite with others and enjoy the thing. And there's also another emotion, surprise. Surprise only lasts a couple of seconds, but it actually acts as an amplifier for what comes next. So if you see a rainbow and you say, oh, let's do that again. If you see a rainbow and your friend says, oh, there's a rainbow, and you go, oh yeah, that's a nice rainbow. But if you suddenly see a rainbow, oh, there's a rainbow, it was nice before, and now it's very nice because you were surprised. So the surprise acts as a multiplier. And a lot of the things that we like to see in the sky, that we go, oh, look, there's a thing in the sky, are things that are not common, not often seen in our skies. So as I said, my friend gets a lot of this awe, but I mainly get that wonder. What is it? How does that thing work? Why can I see that? Where can I see that from? And it's this wonder that has given me the urge at the moment to go off travelling around the world to find things in the sky that I wouldn't normally see. Fortunately, Penguin Transworld have said, we will publish a book if you write this up. So I'm now going around the world, finding these things that are amazing, finding the science behind it, talking to the scientists, and actually taking the reader on my shoulder to say, hey, look at this thing, and here's how it all works. So this talk is based on some of those things for the research I've already done. The book's not going to come out till 2026, so we can wait to EMF 26 before we do any book signings or worry about that. So let's move on to things in the sky. Anyone seen a murmuration? Yep. Now, it's only starlings that murmurate. So this murmuration is when all these birds get in the sky and they do these intricate patterns for what could be 10 minutes, half an hour. And it's only starlings that do this. Other birds do flock, they fly up from the ground, but they generally just go left and right to try and dissuade whatever predator is coming towards them. But it's the starlings that go up into the air and make these wonderful, intricate 3D shapes. So why do they do it? Well, one, it is safety in numbers. The more there are together, if a bird of prey is coming in, it's only going to eat one of them. And so the more there are, and the more eyes that they've got keeping their eyes out for these things, the safer they're going to be. But scientists have also worked out that it's not just for that, it's a massive advertising hoarding. It basically says, come roost with us, we'll be warm together. So all these starlings get together in the winter. Now, in the UK, we have a starling population. But over winter, a lot of migrants come down, starlings come down from Northern Europe, and we get 10 times the amount of starlings over winter. So we've got a heck of a lot more birds, and that makes it much more of a thing to go and murmurate and do your advertising hoarding, come see. So that's why they do it. How do they do it? Scientists have taken videos like this, made all the birds a dot, and actually made a computer simulation of it all. They have discovered that starlings have one main rule. There's no red one, there's no leader, there's no choreographer, there's no plan. Their one rule is stay the same distance away from the 7 nearest birds. So stay the same distance away from the one above you, one below you, left, right, forward, back, and one more to make it a sort of sphere. And that's all they do. And once they've got this rule and they're off flying around, sometimes they need to divert, go one way around a tree or another or a building. So they have a secondary rule for this. If we've got to split, where do we go? Well, we go to where the birds are mediumly dense. Not where it's too few birds, because you might then get picked off by that predator. Not where there's too many birds, because you might actually crash. But that Goldilocks zone in the middle, where it's just right number of birds. The other thing about starlings, compared to the other flocks that come and fly together, is these birds will join in the sky. And you can actually see birds coming in on the wing from somewhere else, and then they join this big flock. Give me a shout if you've seen a rainbow. Hey! So this one was EMF camp last time, and over my tent was not very bright, but a rainbow. I'm sure we've all seen this. Probably the most famous diagram picture of how white light is refracted and split into the different colours. So I remember learning at school that, the sunlight comes into a raindrop, splits, bounces, comes out, splits again, and that's our rainbow. In fact, when I was doing some research for my book, don't ask me how, I found my school notes. My writing's got worse since then, but it's not that good there. In order for us to see a rainbow, there must be rain in front of us and the sun behind us. The light from the sun is refracted as it enters a raindrop, internally reflected, bounced, and then refracted again as it leaves the drop, as can be seen in diagram A. One internal reflection. Dispersion takes place at the first refraction, splits up. When there is dispersion takes place at the first refraction. When there is one internal reflection, the primary or lower bow is formed, and the two internal reflections give rise to a fainter secondary, higher bow. The order of the colour is reversed in the two bows. So have you seen a double rainbow? Yeah. Have you seen that the normal rainbow, it's got red on the top, and then the secondary one, it's blue on the top? They're reversed, due to this lovely diagram. Now there is a little bit more to rainbows than what I learnt at school. And these are two different photos I've taken. And you think, well, why do sometimes we see a little bit of the arc, and why do we sometimes see a much larger arc? Now, it all really depends on where the sun is, where your eyeball is, and where the rain is. Because we're not actually just looking at an arc. We are looking down the centre of a cone. So the rainbow is a cone. You're the tip where the chocolate is in the cornetto. And it comes out, and out where the ice cream would be, there's a fringe all the way round. Like having sprinkles, isn't it, on your cone? And it's that fringe that we see as the rainbow. So it's actually a full circle. Now, if we're high enough up, so the sun's above me, my eyes are here, and the rain is below, we sometimes actually see a whole circle. You might see that also on a waterfall, a whole circular rainbow. If the sun is high in the sky and I'm on the ground and the rain is in front of me, you don't get much of a rainbow because the sun is actually trying to get through the ground, and you just see that small arc. But if the sun is at sunset, so it's really low, my eyes are here, I get the full half an arc of a rainbow. So one thing that we can work from this, if you can see your shadow, and your shadow is longer than your height, you'll be able to see a rainbow. If it's shorter, the sun is too high in the sky, and you won't be able to see a rainbow. There was some interesting maths in that I struggled with. Now if we look at this rainbow, look on the side where you can see on the left-hand side, you can just about see a secondary bow there. In the centre of the rainbow, it's actually quite white. And then after the first primary bow, it gets darker, and then you see the secondary bow. That's really clever too. So, back to my school notes. This wasn't in school. So when the light gets refracted, it can be twisted more one way, but it can't go any further the other. So where it says no light here, you can't get past that red line coming through. And so not much light, well, no light from that raindrop will get to that bit. But that red light could actually be bent all the way inside. And if you mix all the colours, the red, green, blue, all the colours on the inside, you'll actually get white light. So you've got a fringe at the outside where the colours are separated, but bits of, not much, but a bit of all the rest of the light comes in the middle, and you've got those colours mixing again to produce white. So if we have a look again, we've got a lighter inside of a rainbow and a dark band just between the primary and secondary. So that's my second thing. We've done something in the air, the starlings, something in the sky, rainbows. Now let's go up into space. Shooting stars. Who's seen a shooting star? Yay. Who's seen one this bright? No, no, they're not usually this bright. Now, shooting stars, sadly, are not stars. They're actually little bits of dirt, dust, space rock coming down into our atmosphere and heating up and glowing. The way they're coming through, it's not just the friction that's heating them up. They're actually pushing the air as they're coming into our atmosphere. And has anyone used that bicycle pump and it's got a bit hot? It's like that. It's pushing the air, compressing the air, and that's what's getting it hot and starting it glowing. And it does this when it's about 70 to 100 kilometers up. So it's still high in the sky. Now, Earth's not the only place that gets shooting stars. Saturn's moon Titan also gets shooting stars. So most shooting stars come from the dirt left behind from a comet. Comets are basically dirty, big snowballs. And they come from way out, and they're coming in and they pass the sun. As they get nearer the sun, some of the snow, dirty ice melts, but it leaves behind a trail. And the thing with comets is that once they've swung around the sun, they go back out to wherever they go, and then they come back again so many years later, along the same track. So over thousands, millions of years, you've got this same comet coming around and around. And so around the sun, you've got this dirty trail of all the bits of melted comet. Now our Earth goes around the sun, and every so often it crosses one of these paths where that dirty trail of comet. And that's when the dirt hits our atmosphere, or maybe our atmosphere hits the dirt, probably more like that way, and starts to glow. So that's why we get, different times of the year, meteor showers. Now, depending on how much dirt is in that trail, how wide it is, will depend on how long the shower is and how many meteors we can see in that time. If a meteor is brighter than a star or planet, so in this picture, below the big streak that's coming down, you might be able to see the planet Venus. So it's probably about the same brightness there. We call that a fireball or a bolide. If that shooting star, meteor, scientific term for a shooting star is a meteor, is brighter than the full moon, then it's a super bolide. Technical terms for different things. So a meteor that we can see is the size of the diameter of a needle to about a marble. So they're really small. They're very, very unlikely to get down onto the Earth. They'll burn up in our atmosphere. A fireball, which is probably what this photo is, will come down, be between the size of a marble and probably a car. Now, some of those might actually make it down to Earth. Something bigger than that, we're going to have to worry, so I'll come back to that. So the brightness of a meteor, as I said, is probably to do with the size of the meteor and the speed with which we hit it, it hits us. Most meteor shooting stars that we see will be white. If you take a photo, though, they'll come through as different colours. Anyone remember doing this at school? Putting different chemicals in and burning them? Yep. You can actually do it on the fire here. Put some table salt in and we'll get a bit of green. Put a bit of copper in, you'll get a bit of blue. Well, same with the shooting stars coming through the atmosphere. However, because higher up in the atmosphere, the composition of the air is slightly different than it is down here, some of those colours will be just slightly different. So sodium, if there's sodium in the meteor, it will still be the yellowish colour that we're used to. Calcium, though, will be purple, whereas here it's a more orangey red. But meteors generally aren't one element, and so there'll be different things burning up and we'll get different colours up in the sky. So I said most of it comes from the comet. About once a month, a bit of space debris, a bit of old rocket, a lens cap, that will burn up in the sky as well. And about 5% of the shooting stars come from asteroids, which are the big brothers of meteoroids. So we've got some guidelines. If the shooting star is fast and quick, it's a meteor. Shooting star probably came from a comet. If it's slow and steady and leaves a long streak, it's probably space debris. If it's slow and steady and doesn't leave a streak, it's probably a satellite that's still up there. If it's flashing, it's an aeroplane. If it's flashing red, it's an aeroplane. If it's a tight cluster of bright parts coming down, then that'll be a re-entry breakup, probably space debris, but it could be a larger asteroid. And if it's a single object exploding in the sky, then that'll be a bolide meteor. So about 5% of those shooting stars are probably of the larger size. But we've got predictions because, you know, it's really quite worrying. Ask the dinosaurs if an asteroid is coming at us. So we've been tracking the big asteroids, and we know where most of them are. And for a few hundred years, nothing's going to hit us. So we're going to be okay. But there are still some things that are coming in from the direction of the sun where we haven't actually managed to map them too well because the sun's too bright, we can't see them. And actually we've only predicted a few, or we've actually only found a few. Here comes something, oh, it's burnt up, and a meteorite has hit the ground. Now most of these are small things. So these are the sort of things that I've been out looking at, as well as I went to Borneo to see millions of bats coming out of a cave. I've been to India to see the kite festivals. So I've managed to go on a few interesting trips that I'll be putting into the book. But also into the book, I'm putting how can you find some of these things? How can you make yourself a little bit luckier? And actually not just, oh, I wonder if I'll see a shooting star, but actually go out when you're more likely to. So starling murmurations, your local RSPB group will probably have a website that will tell you, oh, they're murmurating over these marshes, or Some human-made structures like piers are actually really good for them, because if you've got 1 million or so starlings come and land on a reed bed, well, the next day all those reeds are going to have fallen over because the 1 million starlings are quite heavy. Whereas if you've got something like a pier, Brighton Pier, it will be there the next day, so they'll come back to the same place. Rainbows, we know we need the sun, we need the rain, and we need the shadow to be greater than your height. Meteor showers. So there's 8, 9, I think, different meteor showers every year where we know we're going to cross that path. One of the better ones is the Perseids in August. So if you find out, Royal Museums Greenwich got a good website on that tell you when to go out and have a look. Now for the aurora, there's an app that I had switched off. It's back on now. That will tell you, aurora's coming, aurora's coming. It's actually quite difficult to predict when the aurora will arrive. Solar eclipses, now they are very easy to predict. Whether it's going to be cloudy or not is another matter, but NASA, various other websites show when that is. The next one that is coming up is 2026 in Spain area. And you can also go out and see the ISS go overhead and see satellite passes. heavens-above.com is a good website for that. So we've gone through a few things that we see in the sky. Excuse me. We know that in order to give us awe and wonder and a little element of surprise to make it all so much better, we just need to be in the right place at the right time. But most of all, we need to look up.